Hello, this is Dr. Mears. Today we are going to be learning about exponential models. Let's go. In an exponential relationship, as one variable increases by 1, the other increases or decreases by a fixed percent. That is the overall what an exponential relationship is. Let's look at some graphs now. So an exponential model has a variable in the exponent position or the power position. It can represent exponential growth or exponential decay. Looking at this graph, this first one, from left to right, which is how we read a graph, just like we read a sentence from left to right, we're noticing this blue curve. This blue curve is the curve of the exponential function. So when we plot points, we're going to get our points in this pattern of this curve. You will notice this green line. This green line is called an asymptote. That means that the curve is going to come close to this green line but never cross it. It's kind of like the point where it cannot go past. So all exponential models have a horizontal asymptote with which the curve approaches but never passes. Here we have exponential decay. Looking at the graph from left to right, we have this blue curve is curving down, it's decreasing. Again, it is approaching this green line, but it's never going to actually cross it. So these green lines are called asymptotes. And these blue curves are the actual exponential relationship. When it goes up, it's growth. When it goes down, it's decay. Let's look at a table of numbers that is going to represent a exponential relationship. And this is going to be exponential growth. Exponential functions play key roles in modeling many natural phenomena. Such models are based upon empirical data. This is empirical data that is gathered. For example, most people know that their chances of getting cancer increases as they age. In fact, by looking at data compiled by the National Cancer Institute, you can readily see that the incidence of cancer increases dramatically between the ages of 35 to 80. So looking at ages 35 to 80, we see 160 all the way up. All of a sudden, we're over 1,800, 1,800. We're almost at 1,900. So here we have the data for females from age less than 1 to over 80. And as you can see, it looks like this would be definitely some type of either linear or exponential relationship. But this is the telling part right here where it's most likely going to be curving up rather quickly. Let's look at the graph of that data. So this is the same data from the table. And we have to notice the incidence of cancer nearly doubles every 10 years between the ages of 20 and 75. So the part of the graph that we're actually looking at right here, between 20 and 75. So this is that graph. So noticing if we cut out this part of the graph right here, we're going to definitely see that exponential relationship where it starts off and then that quick curve up. If we graph the data with age on the X and cancer instances per 100,000 people on the Y, you can see that the cancer instances appear to increase exponentially until 75. So now even expanding this out, so we're looking at down here, now look at our curve. That is definitely an exponential curve right there. Let's look at the equation. So here we have our exponential curve. Here's our equation, y equals a raised to the exponent of x. And this is where our number for a is going to be greater than 1. So we can have y equals 2 to the x. That is an exponential equation. This is our a number, and this 2 is definitely greater than 1. So when a is greater than 1, this number raised to the exponent of x demonstrates exponential growth. All right, how about exponential decay? So we have the HIV virus, which can now be controlled using a combination of powerful antiviral drugs. Upon treatment, the amount of the virus in the bloodstream of infected patients falls rapidly when it plateaus to a level that are difficult to detect with standard laboratory techniques. The following hypothetical data models the typical course of infection for a patient taking a regimen of antiviral drugs for 1 year. So if we look, this is the duration of treatment in weeks, 0 to 50 weeks. And this is the viral load. So this is the virus in the body. So taking the drugs at day 0, this is how much of the virus is in the body, 123,550. So as the weeks progress, we can see that it decreases and holds steady at about 10. So, I mean, even looking at the data, we can see almost a curve here. So that's pretty interesting in how those numbers fall. Let's look to see what the graph looks like. Exponential decay graph. This is the same graph that we just had for our table. If you plot the duration of treatment on the x-axis and viral load on the y, you can study the amount of virus in the bloodstream as it diminishes over time. So you can clearly see that nice exponential decay curve. And this is raised to the 2 to the exponent of x. Okay, so we have exponential decay equation. So this is very similar. This should be an equal sign here. This is y equals a to the x. But in exponential decay, our a, this number right here, is going to be between 1 and 0, 0 and 1. So it most likely is going to be y equals x to the 1/2, y equals 1/2 to the power of x. So y equals 1/2 to the power of x. So this number in decimal point form is 0.5. So this number right here, which represents our a, is between 0 and 1. And so when the number is in between 0 and 1, it's going to be decreasing, which means exponential decay. Just quick linking exponential with geometric sequences. We started with geometric sequences, and I kind of wanted to bring it back, especially since we're talking about the equation. So we see here we have our first term is 1. This is our initial or our start number. So here's our first term. Our common ratio, every time, what are we going to be doing? We're going to be multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2. So we have a common ratio of 2. If we want to write an equation to find the nth term, which you've done in the past, it's going to be u sub n equals the first term times the common ratio raised to the n minus 1. And I want you to notice that the variable n is in the exponent spot. So because this is our a, remember, because our a is greater than 1, this actually is going to represent exponential increase or exponential growth. That's pretty cool how we're now linking it to our exponential functions. All right, grab your GDC, your graphical display calculator, because we are going to be considering the following exponential function. F of x equals 2 to the x. And so what we're going to do is we are going to complete this table, and then we are going to make a graph on our calculator and answer it. We are going to have to answer, does the curve increase or decrease? And is it exponential growth or decay? Well, if it increases, you should know right now it's growth. And if it decreases, then it should be decay. So these will be hopefully easier to answer once we get there. So we have f of x equals 2 to the x. Now, if you remembered, this is actually our a value. And because it's a to the x right here. So that's actually our a value. So we can hypothetically say, since a is great, actually theoretically say, since a, the 2, is greater than 1, it should be increasing, which represents growth. Let's see if we're right, and I want you to practice using the calculator. So what we have to do for each one of these is we have to substitute the -3 in for the x. So this first one right here, it would be f of x, f of -3 equals 2 raised to that -3 power. And so in the calculator, what you would do is you would put 2, and your exponent button, remember, is above the division symbol, so exponent. Not forgetting we have this negative down here, so pushing the negative button and then pushing the 3. So this is going to be 2 raised to the -3, and enter. That's going to give us 0.125. Decimal points are absolutely fine, 0.125. Then we have to do f of -2. So 2 raised to the negative 2, 0.25, f of negative 1, 0.5, f of 0, 1, f of 1, 2, f of 2, 4, and f of 3, which is going to go 2 times 2 is 4 times 2 is 8. Okay, so there you have it. And so what it asks us to do is then make a graph on our graphing calculator. So if you remember, we're going to have to put in L1 and L2. So we're going to press Stat, and then we're going to edit. If you have numbers in here, you're going to have to clear them out. You could press the delete button or the clear. And let's put our numbers in. Negative 3, negative 2, negative 1, and 0.125. And hopefully you're feeling these are increasing. So I think we're going to be growing here. We're going to have it's going to represent growth. And now you have to remember, make sure you press zoom and then 0, and you should have a nice scatter plot coming up. Of course I don't, so let me make sure my stat plot is on. Yup, stat plot is on. Okay. Oh, not zoom 0, my bad. Zoom 9. There we go. Zoom 9. Let's write that down. Don't forget to press zoom 9, everybody, in order to see your graph. Ooh, look at that pretty graph. That is awesome. So let's just sketch the overall, looking at from left to right. We're just going to sketch that upward curve. And I even think this lands on, let's see where it crosses the y-axis, because this would be really nice to know. And it's probably going to cross, I can press trace. Here we go. And it crosses the y-axis at 0, 1. So this is our y-intercept right here. And if you notice that y-intercepts are where x is 0, and then we look to see what the y or the f of x number is. So this is the y-intercept. So if we graph this really quickly, I'm actually going to make this graph. Here's x and here's f of x. I'm going to put a little 1 on this, okay, because that's where it crosses the y-axis. That's very important to know. And then I'm just going to make that curve. There we go. Great. All right, so we can answer these questions. We saw that this is increasing. And since it's increasing, we have exponential growth. Yay. Okay. So let's practice that one more time with, y equals 1/2 x. You can use 0.5 in your calculator if you want, if it's easier for you. But I do want to kind of just go through and relate this back to what value our a represents. So here our a represents 1/2. So a is between 0 and 1. Because 0.5 is in between 0 and 1. So I'm thinking this is going to be decreasing, which means decay. But let's go through and do the work and actually find out. Okay, so again, we're going to have to put in 0.5 to the negative 3, 0.5 to the negative 2, 0.5 to the negative 1. And this is good to do as you're starting to learn about exponents and substitution, substituting all of these numbers in, and writing them out. So you know, when you put in 0, you're putting in 0 where the x spot is. When you're putting in 1, you're putting in 1 where the x spot is. When you're putting in 2, you're putting in 2 where the x spot is. And when putting in 3, you're putting in 3 where the x spot is. And so let's just 0.5 raised to the negative 3, 8, 5 raised to the negative 2, 0.5 raised to the negative 1, oops, clear, 0.5 raised to the negative 1, 2, 1, 0.5, 0.25, and 0.125. Okay, so as you can see here, you're probably getting the feeling as we're coming, this is from the left, remember negatives, we're coming from the left going to the right, our numbers are decreasing. So it definitely looks like exponential decay. So we have kind of two, we're checking now, Our A was between 0 and 1. That represents decrease and decay. Our numbers as we go from -3 to +3 are going down. That represents decrease and decay. So let's check with our graph and see what it looks like. So now I'm going to clear this out. And so let's put in our 8. Okay. Zoom 9, everybody. Ooh, that's a pretty graph as well. Let's press trace. I didn't actually show you this. I know I showed it to you in other videos, but let's press trace. When you press this trace button right here, you see the blinking dot, and you can move over to see where that y-intercept is. And that y-intercept, again, is on 0, 1. Well, x is 0, so here's your y-intercept. So when we're making our graph, x, f of x, and so here is that 1, and instead of increasing, we are now decreasing. So we're going to come in, cross at 1, and just keep decreasing. Okay, so it is decreasing. When you're decreasing, you have exponential decay. Yay! And so that's working with the function, the exponential function, working with the table, putting in our calculator to graph it, and we can see by the equation, we can tell that it was decreasing. By the table, we can tell that it was decreasing, and now definitely by the picture that we made, we can confirm that it was a decreasing exponential function. Let's explore one more way to graph without having to go through the table method, and this is just graphing on your calculator. And consider the following function. F of x equals 3 times, this is times right here, 1/2 raised to the exponent of x. Before we just did 1/2 x, and we saw that graph. Now we're multiplying it by 3. So we're multiplying this whole entire thing now by 3. So I wonder if this is still going to be decay. I'm thinking so, because the a here is raised to the x power. Even though it's being multiplied by a number, that's okay. The a is still in between 0 and 1 because it sits at 0.5. So I'm thinking it still is going to be decay, but let's look to see in our calculator. So these are the steps for your calculator, whether you have the TI on handheld or whether you have it on your phone. What I would like you to do is press this y equals button here, just the y equals button, because we're going to put an equation in. We have to enter an equation into y. So we're going to do 3 times, and we can use 0.5 if you want, that's fine. Or you can just do 1 divided by 2. Either way works. And then we need to use the exponent button. Remember, the exponent button is above the division, so pushing the exponent. And then we're going to use this button right here. This button is the xt theta n button. It has the word link above it, right here, the second one down. And if we push that, we get the x variable. And then you can push the over arrow key. It gets you out of the exponent spot. So after we put the equation in, remembering to use this button as your x, we're going to press zoom 0, not 9. Zoom 0. Zoom 0. Ooh. And now these points were just from my graph before. Sometimes they might show up, but zoom 0 zooms in on your actual curve that you want. So I'm just going to disregard these for a little bit. We're actually going to come back to see what happens when we go from f of x equals 1/2 x to, 1/2 raised to the x to 3 times 1/2 raised to the x. But we're just looking at this blue curve. It is decreasing, and we are able to see that it is decay. We confirmed it here. Let's put the graph in, and I'm wondering if I can just see where the y-intercept is on this. We are going to have to use another system, but I'm thinking it's about at 0.3 here. I'm estimating it. I will show you how to find the intercepts, but that is not today's lesson. Today's lesson was just noticing that this is a exponential decay and decrease of a graph. So we're just going to draw the graph in, sketch it really quickly. You could put y there like I did, or you could put f of x. And here we go. We're just going to go down. I would love to find that y-intercept, but we will do that again in a little bit. There's a couple different ways of finding it, but I'm just going to put what it represents, just kind of how the picture is. I'm going to put decay. Yes, I was correct. Yes. And I followed the graphing step calculator, and I found that it was exponential decay. So this has been your lesson on how to use the y equals to put your equation in and find your graph. And that blue curve is your graph. So now it's time to look at these functions. However, since this video right now is 20 minutes, we are going to have a part 2 of this lesson in which we will finish this slide deck. So I am going to leave you today on looking at these functions, and we will continue this slide in the next video. Thank you very much. This has been your introduction to exponential functions.